Okay. So the paper you have in front of you today, we are looking at square roots today. It's the last thing we got to get in before your state test. All right. Square roots. We all at least should be familiar with the square root button on a calculator. Do we know where that's located? Yeah. I mean, we just used it in the quadratic formula, right? Um, and so we're going to get into a couple things with square roots. Number one, we're going to get into graphing them. What do they actually look like? And that's why you see all of these pictures around the room that have different square root graphs on them. If you look at any one of these, you'll notice that they look different than any other square root that we've done or any other function that we've done to this point this year. All right. This is the last function before your test. We've done linear, we've done absolute value, we've done quadratic, we've done exponential, okay, and now square root. All right, so fifth one that we've got to. What's up? Oh, because after 9 comes 10. There are other things inside of chapter 9 that unfortunately, because of all the stuff that we've gotten through, I've kind of put to the side because I've got to get this part in before your test. And we've also got more things we've got to review. Yes. Uh-huh. Yep. So we're going to look today at graphing a square root. Then next week, we're going to get into simplifying a square root. We're going to get into operations with square roots, meaning what happens if I add them together or subtract them? What if I multiply them? How does that look? All right. Before we get into any of that, though, we've got to first, I think, kind of understand what a square root looks like or what a square root function looks like. So we're going to try to evaluate a square root. We're going to try to graph a square root. I'm be honest with you, I am done with some of you guys in relation to what a domain or a range is. We still are struggling to remember the difference between those two. Can somebody tell me what a domain is? An X value, a range is a Y value, an input is a X, an output is. Give me another set of words that would imply both the same as X's and Y's or the same as domains and ranges or inputs and outputs. There's one more set. I and D, those are your letters. Those are on the x-axis. Independent and dependent variables. Good. So all of those words, okay, if we use the word x value, we use domain, we use input, we use independent, all mean the same thing. Okay, so the moment I see finding the domain, my brain should immediately be saying finding the what? Find the x values. Like, what are the x values? And we're going to see that that's important when you talk about a square root. And then the last thing we're going to get into is a translation of a square root. Translation. Third grade word for a translation. You have three types of transformations, rigid ones. You have translations, you have rotations, and you have reflections. Yeah, when you move it, if you translate it, the third grade word is basically to move it or slide it. Like, it's not going to change the way it looks. It's just going to move somewhere else. Okay. We're also going to take a look at a dilation. If you've been to the eye doctor, you've had your eyes dilated. It's like the worst, right? Your pupil that was super tiny is now the size of your entire eye. And you're right. And you literally are trying to walk out with your eyes closed, walking into things. Okay. But how does that affect a picture when we talk about dilating it? So those are things we're going to look at. All right. So we'll let that go for today because we're kind of short on time. But, can we graph and can we analyze that dilation? Meaning, like, do I know what that's going to look like prior to? Like, some of these around the room, hopefully by the end of the day tomorrow, you should be able to look at them and say, I know what this picture is going to look like. I know where I can find it. And so we get in then to those translations and reflections, right? A reflection is simply a what? What's the third grade word for a reflection? A mirror, to flip it. Yeah, right. Those are things that we could think of as well. So we're first going to start here with a square root. And by definition, a square root function is this: anytime your variable is under the radical. Okay, so if you looked around this room, every square root, the variable's underneath it. Okay? So in these examples here, notice that the variable of x is underneath the radical in each one. But look at this one over here in the non-example category. It sure looks like the variable is underneath it, but actually it's not, right? The line of the square root does not cover the x. So some of you guys whose attention to detail isn't great, you got to be careful there because it matters. All right. If you actually were to graph this equation, y equals the square root of 3 times x, it's actually a straight line. Well, you're close. If you took the square root of 3, it's, the square root of 3 is about 1.7 roughly, maybe a little bit more. Okay. So actually, that's like your slope. But the moment you put the variable under the square root, now you have the ability to change its value. Okay. So for example, take this equation up here at the top. It says that y equals 8 times the square root of x, or 8 radical x. That is the function for speed in feet per second of free fall. All right. So I, the other day, said, well, we have a student who loves to climb trees, and if he climbed a tree without his harness rope on, he very well could experience this. I'm not going to say his name. All right. he could experience the free fall, okay, until he hit that branch or something on his way down, right? Well, every time I change the value of x, I'm now changing the result of the problem. A new input creates a new output. Okay. The higher in the tree he climbs, then the bigger this number gets. And the bigger that square root gets, then the bigger his speed becomes. So if we started with something like this and said, hey, fallen from a height of 16 feet, well, then all I'm going to do in this equation is plug in a 16 where the x was. If I input a value, I should be able to output a result. Now, we all should know what the square root of 16 is. 4, and 4 times 8 is 32. So in this particular case, falling from a height of 16 feet would result in a free fall of 32 feet per second. Essentially, you've created an ordered pair, right? A height of 16 created an output of 32. If I increase the height, what happens to the output? It should increase. You fall from a higher distance, you should fall faster. Okay? So if I change it from 16 feet to 20 feet, I could expect the answer to be what in relation to 32? Should be higher. Okay. Now, the problem here is when I input a value of the square root of 20, does anybody know the answer to the square root of 20? It's a decimal. Yeah, right. When I take the square root of 20, I end up with a decimal. What do I get? 4.5, and your screen is full, right? What kind of number is that when your decimal doesn't repeat, doesn't terminate, but fills the entire screen? Starts with an I. No. I know you put the line. I, R, and then an R. Irrational, irresponsible. No, it's an irrational number. Okay, so in this case, John, you said it was 4.5, and it continued on past that point. But if it says round to the nearest tenth, I would take 4.5. So then it becomes 4.5 times what? Times 8, and you get an answer of 4.5 times 8. 36. So I get an answer of 36. And again, it's still feet per second. But I get a new ordered pair, right? 20 is now paired with 36. What's up? Yeah, so your calculator is simplifying the radical. Okay, and that's something we're actually going to talk about on Monday, which is nice that your calculator does that. Well, unfortunately, you don't really know what it means, and that is kind of problematic. But we'll get more into that. It's actually simplifying it. It's found a perfect square inside of it. We're getting there. We're not there yet. We will be on Monday. Not there yet. Okay. Now, When you start talking about square roots, there are certain numbers that you cannot square root. Can you tell me a number that you cannot square root? You can square root 13.
100.
I'm pretty sure you can square root 100. A negative.
A negative.
Destiny? Try it.
Oh, you can't do 100.
You still get 0, so I can square root 0,
What about negative 0?
but I can't.
No.
Well, there is no such thing as positive 0 or negative 0, so even though you typed it, I think your calculator just disregards it. You can't put in a negative, right?
Mom, give me an answer.
Because if you multiply two numbers by each other, whether they're negative or positive.
Wait, why does it say?
Because like two negatives make a positive, and two positives make
Oh, just say
Oh,
domain error.
okay.
It says
Oh.
if you change the modes, then it'll do it.
Okay, right, because now you're getting into imaginary numbers. That's not that's not for you yet. Okay, yet. All right. Now, if you go back a second, and Ruby and I think Emily, you were on that same page there. When you start talking about negative numbers, the only way to produce a negative is with a positive and a negative. But a square root is not made up of two different numbers. It's made up of the same number, okay, an identical number. And so, at least on this TI-30 calculator, when you type in the square root of a negative number, your calculator actually says a domain error. What is a domain? An X value. It's essentially saying you inputted a number that's causing an error. All right. And so when we talk about finding domain values of a function, of a square root function, we have to think about this statement here. You can't let your square root produce a negative result because that's not possible. So when I choose values to input, I have to do it carefully. All right. And so on your paper, you have 3 graphs available. On your first graph, I would like you to put this equation here, this function, y equals 1 plus the square root of x minus 4. Now, what's that? Depends on which way you want to put it. Whatever makes you happy. Put your graphs on the right or put your graphs on the left. I don't care. So ask yourself this question. What's the first value that I could put in for x? Meaning, what's the first value that I could put in for x that would allow this function to have a result? Well, if I put in a 0, 0 minus 4 is negative 4. You allowed to take the square root of a negative? No.
6.
Okay. Emily's like, darn it, it's 4, right? Okay. So, in theory, there's an infinite number, right? 4 works, 5 works, 6 works, 26 works, 100 works. But the first one that works is 4. All right. You need to focus your attention to that portion right there, the part that is under the square root. And putting a 4 in there is the first value that'll work. Because when I do 4 minus 4, I get 0. When I take the square root of 0, I get 0. Plus 1, I get 1. So there is my first input and output. I put in a 4, I get out a 1. What's the next number I should choose to input if I know that 4 is the first one that works? I should put in a 5. Now, if I put in a 5, 5 minus 4 is 1. Square root of 1 is 1, and 1 plus 1 is 2. So my next output is 2. Now I'm going to tell you right now, the next one cannot output a value of 3. Yeah, why not? If the values of y went 1, 2, 3, what are you creating? You're creating a line, and this is not a straight line. It's not linear. It's called a square root. It better not produce the same looking picture. Yeah, good. So put a 6 in here. 6 minus 4 is 2. Now you're going to need a calculator here. What's the square root of 2? 1.4, roughly, right? There's more, but we'll just round it to 1.4. And then I have to add 1, so I get an answer of 2.4. Okay. What's my next input number? 7. Once you figure out where it starts, no problem. You're just going to kind of run the pattern from there. But we got to figure out that first input value that we can put into the function. So if you put a 7 in, 7 minus 4, 3, square root of 3, 1.7, add 1, 2.7. And then 8 will be the last number I choose. Excuse me?
What?
You say negative 3?
8 minus 4.
3. Okay. Now listen, if I'm going 1, 2, 2.4, 2.7, my answer better not be less than 2.7, right? And that answer does come out to be a 3. All right. Now I just need to graph it.
Okay.
It's not hard. Okay. So it starts with the ordered pair 4 and 1. And then it goes to 5 and 2. Now here it's going to start to climb, but not as much. So now it's 6 and 2.4, and then 7 and 2.7, and then I get 8 and 3. Why did I not choose values of x that were smaller than 4? Because I can't have a negative, which means this graph doesn't go in both directions. It only goes to the right. The y value could be negative. Absolutely. Okay. And you'll see some of those around the board. Like if you look at the question over there next to Evan, notice that the square root of the problem there right in front of Evan has a negative in front of the square root. So whenever you get an answer, you're going to force that answer into being a negative, which is why if you look at, take this one over here by Logan, for example, notice that instead of going off to the right, it goes off to the left, because each time you get an answer, it's a more negative number, something further away from 0. So instead of traveling to the right, like our example on the board does, it travels to the left, following that one. Okay. Well, it all depends on what this expression on the right-hand side looks like. So notice around the room, they are all different, right? Some of them involve, here, this one involves subtraction, but then another subtraction outside of it. Some of them like that one over there on the sideboard. Notice it has a multiplication outside the square root and then a subtraction. So you're changing that result based off of what happens. But it all starts right in the middle here by you figuring out what's available for the domain, for the x values. And so if you look at your homework, you'll see that not only do we have to graph it, but then they're asking us for 2 other things. Can I identify the domain? And can I identify the range? Now, truly, we've already done this when we figured out what values we wanted to use. The first value that Emily was just adamant that we started with was what? Was 4. And after 4, we went to 5, 6, 7, right? So my domain statement is going to reflect that my x values have to be greater than or equal to 4. That's where it started. What would you say for your range? You wouldn't say the same thing because the range doesn't talk about x. It talks about your y's. So my statement there would say what? Y is greater than or equal to 1. Very good. Okay, it started at a value of 1, and the next value was bigger than 1, and the one after that was also bigger, and it just continued to go in that fashion. All right. So we're just going to look at one more. I think that'll be enough for us to get the hang of what's going on for right now. All right. But again, as you look at this problem, you need to focus your attention inside the radical. What's the first value that you can use that will not let this be a negative? Last time I used 4 to start with. Would I put a 4 in this one? If you put a 0 in here, 0 plus 3, that's 3. 3 times 4, that's 12. That's way bigger than where. But don't just give me something. Every one of these pictures has a starting point. What's that starting spot? -3? Why do you think that? Oh, you just randomly picked a number? Well, Emily, if I put a -3 in there, what's -3 plus 3? 0. What's 0 times 4? 0. Can you take the square root of 0? Yes. Could you take something smaller than that? No, because anything smaller than that would give you what kind of answer? A negative. So I know that this does start at -3. That is the first value that works. Now, for my next domain value, should I go to -2 or should I go to -4? Which way should I go? Why not -4? Okay, so if I went to -4, what's -4 plus 3? -1, and -1 times 4 is -4. Can you square to negative? So nope. So I'm going this way: -2, -1, 0, 1. I would say right now you should be able to tell me what your domain is. That x has to be what? Did my numbers get bigger or smaller? Well, which way did they go? They got they got bigger, right? So x is greater than or equal to -3. Now I just need to get some outputs, some answers on the other side so that I get some ordered pairs. First one will be 0, yep. Because if you put in a -3 and you added 3, that's 0. 0 times 4, still 0. Square root of 0, still 0. What about your next one? What is it? 2? How'd you come up with that? I don't know. Plugged it all in, hit enter. -2 plus 3 is 1. What's 1 times 4? 4. Square root of 4 is... That's how you got an answer it too. Yeah. Anybody got the next one? Oh, no? Faith? 2.8. Very good. So if you had put a -1 in there, and -1 and 3, that's 2. 2 times 4 is 8. Square root of 8 is 2.8. Yes. Next one is what? 3.5, I think, if you round it. And last one is 4. Okay. So if you graph this one, starts to the left at -3 and 0, and then it goes -2 with 2, -1 with 2.8, 0 and 3.5, 4 and 1. Does my arrow go off to the right or off to the left? To the right. That's where this graph is headed, off to the right. Now you compare these two. This one is more vertically stretched. It's taller than the other one. How come? What made that happen? That's okay. What happened? There was something that we did in this one that we did not do in the last one. We multiplied, right? We multiplied by 4, and that produced bigger numbers. And when we multiplied by bigger numbers, we got bigger results. And that caused my y values, my outputs, to be further apart, which stretched it out. If I would have divided, then my answers would have gotten what? Smaller. And so that's not a vertical stretch. They actually call that a compression. You ever feel like your back's getting just like smashed throughout the day?
Right now.
Right? Like your spine is compressing. Okay. They actually say in the morning you're almost like an inch taller in the morning than you are in the afternoon by just the compression of your body all day long. Okay. So the multiplication is that stretch. The division would be that compression. And there's nothing to do here. I just want to show you this so you kind of get an idea. We can stretch vertically. We can smash like vertically as well, that compression. And we can also shift in different directions. Now, a parent function is kind of like the beginning, the original. So for a square root, it's one that comes right out of the origin, and it has a whole bunch of perfect squares in it. Like look at this order pair, 1 and 1. The next order pair is 4 and 2. The next one after that would be 9 and 3. The next one would be 16 and 4. 25 and 5, okay? So that's the parent function. That's kind of like the original. Here are two different things that could happen as well. If you put a number after the square root, so if you add something or you subtract something, if you add, pushes it up that many units. If you add 2, it pushes it up 2. If you take away 1, it moves it down 1. So it just shifts it. It translates it up and down. Look at this. If you put a value inside the square root, then it moves it left or right, but it actually moves it backwards of what you might think. Look, a plus 4 actually moves it to the left 4 because that's what you need to make it equal to 0. You need that opposite in order to make it equal to 0. So if you said like minus 1, then it actually pushes it to the right 1. So look at the graph in the back between Maddie and Courtney. It says underneath the square root x minus 6. That would actually push your graph which way? Would it push it up? Would it push it down? Would it push it right or push it left? Look at this picture up here and tell me, the graph you see in the back, does it more closely mirror this over here on the left, or does it mirror the one on the right?
It's like upside down.
No, not the picture, the function. The one at the bottom, the one that says the square root of x minus 6. It matches the one on the right, right? Because the number is under the square root. Now, if it's plus, it goes left. If it's minus, it goes right. So that one says minus 6. So it should be something to the right 6 units. So if you looked around this room, you probably could find this graph by just realizing it's something that's been shoved off to the right 6 units. Okay. What's that? You can't see that far? All right. So tomorrow when you guys come in, you guys are going to do like a little scavenger hunt of these different ones around the room. But tonight, okay, you have 5 questions on the front. Should take you less than 10 minutes, all right? And you'll still make your banquet on time, all right, John? All right. So those 5 questions before tomorrow.